everyone, Matt here. In the last episode, we talked about the difference between validity and strength when it comes to deductive and inductive arguments. In this video, we're going to talk about what's called the counterexample method, and it is a way of proving that a deductive argument is invalid. So without further ado, let's get started. The first thing that we need to know is that the validity of a deductive argument is determined by what is called the argument's form. Sometimes this is called the argument's structure. And so in order to prove that an argument is invalid with this method, we first need to understand how to figure out what the argument's form or structure is. All right, let's take a look at this example. So in our first premise, all snakes are reptiles, and we conclude that all snakes are cold-blooded. Well, you might think that this is a valid argument, but as it's written, it's not formally valid, what is called formally valid. And if you think about it, you can see that we're actually missing a step in the argument that connects cold-bloodedness to snakes. So we've got that snakes are reptiles, and we've got that snakes are cold-blooded, but we've got no connection between the first premise and the conclusion. We need something else in order to connect this, and the most obvious premise, or the most natural way of saying this, is to say something along the lines of all reptiles are cold-blooded. And when you do that, then you're connecting the first premise to the second. So we've got the reptiles from the first premise in the second one, and the cold-blooded from the conclusion in the second premise. So there's that connection. And then we can say that the argument is formally valid. So what do I mean by formally valid? So here's a rewritten statement of this argument that is now formally valid with the added premise. And in order to understand the argument's form, you first have to do what's called isolating the form of the argument. In order to isolate the form of the argument, we must uniformly substitute letters or variables in for the terms or content of the argument. Now we're going to be using capital letters as variables, and they work a lot like variables work in mathematics. So if you have to solve a math problem for x, then the x is a variable, which is either an unknown or it could stand in for anything. So it's the same idea here, where we're going to plug in a letter for the content of the argument. This is an example of a categorical syllogism. So categorical syllogisms are composed of categorical statements. We've talked about these in previous videos. But a categorical statement is just a statement that relates to categories of things. So in the first premise, we're relating the categories of snakes and reptiles. The second one, reptiles and cold-blooded things, and so on. So what we're going to do when we isolate the form of a categorical argument, we're going to plug in letters for the terms. And when we do this, we want to leave the other words, the connecting words like are, and the first word of these categorical statements, all. The first word of a categorical statement is called a quantifier. So in this case, all of our quantifiers are all. So the quantifiers need to remain the same in the form of the argument, and the verb, which in a categorical syllogism, the verb is called a copula. So the copula must also remain in the form of the argument. So for instance, here's the way we're going to do this. The first premise, we're just going to substitute snakes for A and reptiles for B. Now once you have determined that a particular letter is going to stand in for a particular term, everywhere that term reoccurs, you must use the same letter. So in the second premise, we used B for reptiles because we used B for reptiles in the first premise. So once you determine that you're going to use that letter for that term, everywhere that term reoccurs, you got to use the same letter. All right, so here is the form of this categorical syllogism. We've uniformly substituted in letters for the terms in the argument, and we've kept all of our quantifiers the same. So we've got alls here, and it matches up here, so all. And then our verbs are also the same. The copula, are, is the same in all of these. So we've got are here. And our terms are correct. So we used A for snakes, and we used A for snakes down here. And we used C for cold-blooded, C for cold-blooded. Now when you do these on your own, it doesn't matter what letters you choose. You can choose whatever letter you want. When you're working in MindTap, sometimes they will tell you what letter to use. So just make sure you use the letter that MindTap tells you to use. But for our purposes, you can either choose random letters like A, B, C, X, Y, Z, or you can use letters that remind you of that term. So we could have used S for snakes, R for reptiles, and so on. It doesn't really matter. All right, this is the argument form. This one is a valid form. So the counterexample method doesn't work on valid forms. You can't prove that an argument is valid with the counterexample method. You can only prove that arguments are invalid. So we're not going to try it out on this one since it doesn't work. So the key terms when we're talking about the counterexample method, we're going to be talking about substitution instances. And a substitution instance is what we have when, let me go back. We've got our argument form here, right here. A substitution instance is when you plug in other terms for these letters. When you plug in other terms for these letters. So we could theoretically plug in any terms we want for these letters. We'd have a different argument, but it would be the same structure or form of the argument. And it doesn't really matter. We could say something like, all dogs are mammals, all mammals are warm-blooded, therefore all dogs are warm-blooded, and so on. Just use your imagination. So that's a substitution instance when we plug in other terms for the letters of our form. Uniformly. So remember, if you substitute in a word like dog for A, then everywhere A is reoccurring, you have to use dog again. Now a counterexample is a special kind of substitution instance. And this is the important part for the counterexample method. We want to have a substitution instance where we're plugging in other terms for the letters, and we want the premises to be true and the conclusion to be false. And the reason why we want this is because of the nature of validity. If an argument is valid, then it's going to be impossible to come up with a substitution instance with true premises and a false conclusion. So let's go back. I told you this one was valid. It's going to be impossible to plug in other terms for A, B, and C in this argument and come out with true premises and a false conclusion. You can sit here all day, every day, for the rest of your life, thinking of every single different possible combination of A, B, and C, and none of the substitutions that you pick out are going to give you true premises and a false conclusion because this one's valid. All right, so that's counterexample. Let's do an example. So this is another example. The form of this argument is slightly different than the form of the last one because we've rearranged the argument. So if we were to isolate the form of this argument, we can use A for snakes, B for cold-blooded things. We can use C for reptiles. Now, notice I already used B for cold-blooded things, so I must use B for cold-blooded things in the second premise. And I used C for reptiles, so I got to use C for reptiles here. I used A for snakes, so I got to use A for snakes here. Now, this is an example of an invalid argument. And the way that we're going to prove that it's invalid is we're going to come up with a substitution instance. We're going to plug in other terms for A, B, and C, and we're going to do it in such a way that the conclusion is false and the premises are true. So this is the way it has to work. Not one of your premises is true, but both of the premises must be true and the conclusion is false. And the way I recommend that you do this is that you always should start with the conclusion and make the conclusion false first. So think of this as blanks. So what can you say that's false in the form of all blank are blank? It doesn't have to start with the letters A and C. It can be any term that you want. And it's probably, some students have a hard time of saying false things or thinking of false things because normally when you're in school, you're only supposed to be thinking and saying true things. But now you're allowed to say something false. So just off the top of your head, what can you think of that's going to be false in the form of all blank are blank? Sometimes it helps to think of categories of things like the animal kingdom where there's clearly defined terminology and categories. So let's stick with the animal kingdom for now. One example of a false statement might be all dogs are cats. So that's an example of the all blank are blank form, and it's false. So once we have determined, we've got our false statement down here, all dogs are cats. We use dogs for A. So now we just plug in the A and the C up here in the premises. So all dogs would be here in this premise are blank, and all cats are blank. And so now all we have to do is think of something that we can plug in for B that will make these two premises turn out to be true. So all dogs are blank, all cats are blank. What's going to be true about both dogs and cats? Well, there's lots of things. Whatever pops into your head first that's true about both of them. They're both mammals. They both walk on four legs. They both have tails. They both are pets. Anything you can think of would work as long as it turns out to be uncontroversially true. So let's just use mammals. All dogs are mammals, true. All cats are mammals, true. Therefore, all dogs are cats. That's false. So now we have a successful counterexample. We've plugged in other terms for A, B, and C in such a way that give us true premises and a false conclusion. So this is the method that we're going to be using. Our first step is always to isolate the form of the argument, using letters to stand in for the content or the terms of the argument. My recommendation after that is to start with the conclusion and make it false. So what kind of substitution instance can you use to plug in for those letters that are going to make the conclusion turn out to be false? Once you've made the conclusion false, then use the terms that you've used for those letters in the conclusion to fill in the rest of the argument. Once you've done that, you should only have one term left that you need, and that's the term that you want to plug in to the premises to make the premises turn out to be true. So that's what our third step. Figure out what you can plug in for the third variable that will make the premises true. And that's it. Once you've done that, you've got true premises and a false conclusion, you have a successful counterexample. Now, one note. I mentioned this before. This strategy can only prove that an argument is invalid. If you're sitting there working on an argument for homework and you've plugged in a bunch of different terms for these letters and you can't figure out one that makes true premises and a false conclusion, that doesn't prove that it's valid. This can only be used to prove that an argument is invalid. And all the examples that we're going to be given in the homework and in these examples I'm going to go over, I'm telling you now, they're invalid. We're just going to prove that they're invalid. So let's do another example. Here's an example of an argument. And this one starts with a conditional claim. So the last argument we did was a categorical syllogism. This one is a slightly different form of argument. So we've got our conditional statement. We've talked about conditionals before in previous videos. If you don't remember anything about them, you probably need to stop and go back and look at those videos. In a conditional statement, we've got different parts. The part that follows the if is called the antecedent, and the part that follows the then is called the consequent. So when you look at this argument, it seems like it might be a really complicated argument. You might not even be sure how to isolate the form of this. And so it seems complicated, like you want to say, if A of U is R to W, that's way too complicated. Whenever you see a conditional statement, all conditional statements are going to have a really simple form or structure. You're going to use one letter to stand in for the antecedent, the part that follows the if, and you're going to use another letter that's going to stand in for the consequent, the part that follows the then. So we'll have one letter to stand in for all of this part right here. The airspeed velocity of an unladen swallow relative to its weight is the antecedent, from if all the way to comma. So we need one letter for that. And then the part that follows the then, the consequent, heavier swallows will be slower than lighter swallows. We need one other letter to plug in for this. Now once you've determined these, notice these two, the second premise and the conclusion, are just restatements of the antecedent and the consequent of this conditional. So once we've picked out a letter for heavier swallows will be slower than lighter swallows, we use the same letter for this because that's just a restatement of the consequent. So our form is going to look like this. It's actually very simple. If A, I picked A because it reminds me of airspeed velocity of an unladen swallow. And I picked H because we're talking about heavier swallows here. So all conditional statements are going to have a similar form. If blank, then blank, because we're using letters to stand in for the antecedent and the consequent. Now once we've isolated the form of the argument here, if A then H, the second premise is a restatement of H, then the conclusion is A. You might not, just looking at this, you might not know if this is a valid argument. But once you've isolated the form of the argument, we'll be able to prove that this is an invalid argument form. Now this one is a little trickier because I told you we should start with the conclusion and make it false. Well, that's still true. We still need A to turn out to be false. But now, since A has to be false, A must be a complete sentence. So in the categorical syllogism argument that I showed you, we just had single words or terms. But in this argument, since A's got to turn out to be false, we've got to have a complete sentence, a statement that is false for A. And then we're going to plug that same statement in here for the A and the antecedent of the conditional. And then we've got to have another statement, H, that's true. So here's a trick. When it comes to conditional statements, and we're saying that we need to come up with a false statement here, what you need to do, or one way that I like to think about these, is once I make this a false statement, then I imagine what the world would be like if that false statement was true. So we've got our false statement here. If that false statement was true, then what? And what would follow from that? And then I try to pick something that would be true anyway. And then I know that this is going to be true, and this is going to, because remember, H has to be true as well, but A is going to be false. So what's an example of this? Well, this form of argument actually has a name. It's called affirming the consequent, because we are affirming the consequent in the second premise here. And whenever you see affirming the consequent, I have an example of affirming the consequent that helps me remember. So here's an example of a counterexample for this claim. I'm going to start with a false claim here. Adolf Hitler was beheaded. That's false. He was not beheaded. So now, think about what would be true if Adolf Hitler was beheaded. Well, if the world was like that, then what would be true is that Adolf Hitler would be dead. And it just so happens that Adolf Hitler is dead. So our second premise is going to turn out to be true. So our new argument now is going to be, if Adolf Hitler was beheaded, then Adolf Hitler is dead. Adolf Hitler is dead. Therefore, Adolf Hitler was beheaded. So we've got our successful counterexample. I call this the Hitler example, that proves that affirming the consequent is an invalid argument form. So just remember, start off with a false conclusion and then work your way backwards for the rest of the argument. So let's look at some more examples. Here's an example of an argument. This is another categorical syllogism. And this one is slightly different than the last one. So in the last one, all of our quantifiers were all. Remember, the quantifier is the first word of a categorical statement. Now we have a different quantifier, some. So we have to make sure that that sum occurs in the form of the argument. Our copulas are all the same, R, and R. And we've got another sum here. And we've got all here. So when we isolate the form of this argument, I'm going to plug in letters for the term, snakes, venomous creatures, and rattlers. But I want to make sure some R and all occur in the form of the argument in the same way. So the form of the argument is going to look like this. Some S are V, all R are S, therefore some R are V. So that's the form or the structure of the argument. Now, we can come up with a counterexample, and I'll show you in the next slide. So I've already put it up here. We've got our form that's the same as it was in the last slide. And in this part, I've left these blank. We need something to plug in for these blanks. If we start with the conclusion and make it false, some blank are blank. So what could we plug in for R and V that are going to give us something that's false in this conclusion? Some blank are blank. Well, just think about it. What can you say that's false in that form of some blank are blank? You might be able to think of a lot. There's a lot of examples of these if you sit here and think about it long enough. Well, we talked about animal categories. We've talked about Hitler and beheading. Let's talk about a different category of things, because it's helpful to think about these things in categories. Think about the category of automobiles, vehicles that are made around the world. So there's clearly defined categories, brand names, different kinds of vehicles. So you could say something that's false in the form of some blank or blank like this. Some Toyotas are Fords. That's false, because there are no Toyotas that are Fords. They're different companies. So if we do that, some Toyotas are Fords. We've used Toyotas for R and Fords for V. So up here, we've got to make sure Toyotas occurs for R and Fords occurs for V. So now all we have to do is figure out this third variable and make these turn out to be true. So some blank are Fords, all Toyotas are blank. What could we plug in for S? One thing we could use, there's probably several different ones you could use. Think of things that are more broad in category. What's true about all Toyotas? Well, all Toyotas are vehicles. That's true. What's true of some Fords? Some vehicles are Fords. There are vehicles besides Fords. So some vehicles are Fords. All Toyotas are vehicles. Therefore, some Toyotas are Fords. These are true. This one's false. There's lots of different ways you could work this out, and you'll get the right answer, as long as what you plug in for S, R, and V make the premises true and the conclusion false. All right, here's another example. This one's not in premise conclusion form like we've seen before with numbered premises, but we can still do the same thing. Since some nerds are not logic teachers, so notice that we've got an indicator word here from one of our first lessons. Since is a premise indicator. Since some nerds are not logic teachers and all philosophers are nerds, we may conclude that. That is a conclusion indicator. Some philosophers are not logic teachers. So in this one, this is another categorical syllogism. We've seen these quantifiers, some and all, but now we've got a different copula. In this premise, the not is included in the copula. So this is why copula is a little bit different than verb, because the verb is still are. But in categorical statements, the copula includes not in a statement like this. So right here and right here, that not, whenever you've got a no or a not in your argument, it's got to show up in the form, because no's and nots are important. Do not let them be absent from your form. So here's what our form's going to look like. I use N for nerds. Some nerds are not logic teachers, so L's logic teachers. All philosophers are nerds. Some philosophers are not logic teachers. Okay, so here is our form. Now, we're going to do this in the same way that we've done the previous ones. We're going to start with the conclusion first, right here. And we need something of this form that's false. Some blank are not blank. So now we got to think of something that's false in that form. Some blank are not blank. Well, what can you think of that's true in that form? Some blank are not blank. Well, depending on what category you like to think in, we could think of in the animal kingdom. Some mammals are not warm-blooded. That's false. You could think in the category of cars. Some Silverados are not trucks. Or some Tacomas are not trucks. That's false. So we've got a couple examples of statements that are false in that form of some blank are not blank. Think about maybe more specifically. How about fruits? Some apples are not fruits. That works. Some bananas are not fruits. That works too. So now, depending on which one we want to choose, let's just go with our some mammals are not warm-blooded right here. So we've got P here, mammals. L is warm-blooded up here. So now we need something for N that's going to give us true premises. So all mammals are blank. Some blank are not warm-blooded. What could we plug in for N that's going to make those true? Well, there's lots of different kinds of animals besides mammals. There are bigger categories that mammals are a part of. So let's think of this second premise first. What's true of all mammals that's also not true of this thing when it comes to being warm-blooded? Well, one of the bigger categories that mammals are in is animals. Mammals are animals. So we could say that all mammals are animals right here for this premise, and that's true. Some animals are not warm-blooded. That's also true because there's cold-blooded animals. So now we have a successful counterexample by starting with the conclusion, plugging in the things we've got here, and then figuring out our third variable. Here's another example. This will be our final example. We've done categorical syllogisms. We've done arguments with hypotheticals or conditional claims. Now look at this one. This is a disjunctive claim in the first statement. And disjunctions, so again, this one looks kind of complicated, but disjunctions are simple just like conditionals are simple. So with the conditional, you just needed a letter for the antecedent, you needed a letter for the consequent, and you were done. For a disjunction, a disjunction is just a fancy logical term for an either-or statement. And the way that you isolate the form of a disjunction is you look for the things on either side of the or. And we just need one letter for one of the things on the left side of the or, and we need a different letter for the other thing on the right side of the or. Now, in fancy philosophical terminology, the things on either side of the or are called disjuncts. So we've got one letter for each disjunct. And what looks like a complicated statement is actually really simple, either W or H. I use W for the velocity of an unladen swallow is proportional to its weight. And I used H, and I used H for it is proportional to its height. And this one is a restatement of it is proportional to its weight. So I'm just going to use that letter again. And this one is a restatement of it is proportional to its height, where I'm going to restate that letter again. So now we have the form of our argument, and we're going to use the same technique. We're going to start out by making this conclusion turn out to be false, then plugging it in here, and then come up with something true for W. So some students are confused about this, because if we have something that's obviously false here, is this going to be true? And the trick when it comes to disjunctions is, as long as one of your disjuncts is true, the whole disjunction is true. Doesn't matter what H is. As long as this is true, W, the whole thing is true. So as long as you pick something that's true for W, a whole statement that's true, then this is going to be true. And we pick something that's obviously false here. And there's lots of examples. So just say any sentence that's false. Like, I am the President of the United States. Our first premise, if that's true, is either Donald Trump is the President of the United States or Professor Flumber is the President of the United States. Well, Donald Trump is the President. That's true. Therefore, Professor Flumber is the President of the United States. That's false. So we have a successful counterexample. And you can probably think of other examples for H and W, where these are going to be, W is going to be true, H is going to be false. And because W is true, this whole one is false. All right, that's the counterexample method. We went through what it is, several examples. So if you have any questions, let me know. And in the next video, we're going to talk about extended argument patterns.